Hello. Today we're going to learn about solving right triangles and inverse trig functions, and they're practically the same thing. In fact, I bet you never knew that a right triangle was a problem that needed to be solved. How many times have you looked at a right triangle and said, how do I solve this? Probably none. What they mean when they're talking about solving a right triangle is coming up with all the angles inside the triangle. It's no big deal. Don't know why they even have a special phrase for it. Why don't they just say, find the angles in the right triangle? I think this has historical reasons. It probably meant something important a long time ago. Now, it's just an inverse function. And remember, your inverse functions from algebra, for instance, if you had f at x equals x squared and g at x equals square root of x, then you can put them together and if you evaluate f at g, you just end up back at x. The inverse is the one that gives you back what you started with, the x. For instance, remember in numbers we have inverses like a, and then the inverse is 1 over a, and if you multiply them, you just get back to 1. Well, in functions you have inverses. They're the ones that just take you back the other direction. If you're at x squared, you want to go back to x, you take the square root of x. Well, it's the same thing over here. And by the way, this negative 1 over here, this doesn't mean 1 over the tangent. Frequently, again, if I write a inverse, that means 1 over a. Because the inverse of a constant, a simple number, is 1 over that number. But the inverse, this also means the inverse of the function, but it doesn't mean 1 over the tangent. It's a different type of inverse. So what this all comes down to is, in a sense, kind of easy. We already know that, say, the tangent, say, for this angle is y over x. Now what's the inverse tangent? The inverse tangent of alpha? We can't talk about the inverse tangent of alpha. Remember, tangents only apply to degrees. So the tangent of something like, say, y, that wouldn't make any sense. That's a length. Well, along the same lines, the inverse tangent wouldn't make any sense to put an angle measure in here. It would always be a ratio or something which corresponds to a ratio. And it yields the outcome, the image of the inverse is the angle. You get the angle back again. So if you were to say, take the tangent of the inverse tangent, you would just end up right back at alpha. You just end up back where you started. So if you want to know what y over x is, you take the tangent of this angle. On the other hand, if you have this angle, then you take the inverse tangent. And in some books, you will see this term. Arc tangent. Same thing. That means the inverse tangent. This is like old-timey talk for inverse tangent. They used to say arc tangent. And the same thing is true for the sine. They would write arc sine. Same thing as sine inverse. I don't think we'll be using those terms in this book, but if you run into them, don't be confused. It just means inverse function. And the same thing is over here. For instance, sine of alpha. That's just y over h, right? Opposite over hypotenuse. Well, the arc sine of opposite over hypotenuse will give you back alpha. So if you're probably becoming kind of obvious to you that these inverse functions are used to find angles. Trig functions were used to find ratios. Now if we have ratios, we can use those ratios to work backwards to get the angles. And that's what the inverse functions do for us. It's really pretty simple. And if you're wondering how to compute these inverse functions, well, we compute them pretty much the same way we did with the regular trig functions. We plug them into a calculator. And if we happen to have, when we did it originally with tangent, sine, and cosine, if we happen to have actual numbers here, we could work out what the ratios were. Frequently you don't. You just have the angle, and then you punch it into your calculator. And for the inverse tangent, there's hardly any choice but to punch it into a calculator, or in the old days, you look it up in a table. For alpha, it's kind of easy to define a ratio, and if you happen to know the dimensions of the right triangle, you could work it out. But it's pretty hard to find a formula given, say, the tangent, so you know what the ratio is. And remember, the sine and cosine are restricted. They don't get any bigger than 1. But the tangent, that goes from minus infinity to plus infinity. Although in this course, it'll just go from 0 to plus infinity. That means you could stick absolutely any number in here. And you could evaluate the inverse tangent of that number. Since there are no restrictions, it's pretty hard to look at this number and come up with some kind of a formula that's going to give you alpha. However, as long as you've got a calculator, you've got no problem. And that's all anyone's ever going to expect you to do. No one expects you to be able to figure out what the arc tangent, arc sine, or arc cosine of these are. Some of them you will get to know just because you'll use them. If this were, say, the sine of 0.707, well, people who study trig a lot automatically know that means that the angle is 45 degrees. And there are several of them like that. People will be aware of the sine of 30 degrees, 60 degrees, 45 degrees. When you study trigonometry more extensively, you'll learn to just memorize what the sines, cosines, and tangents of some common angles are, and you will be able to instantly spot the arc sine, or the inverse sine, inverse cosine, and inverse tangent. But you're not really working out an equation which leads you to it. You just know what it is, if you see the difference. At any rate, all anyone will ever expect you to do with these inverses is punch them into a calculator. Once you've set up your equation, you will just use your calculator to figure out what the inverse function is. Okay, now that we have explained these inverse trig functions, they're not really that tough. The calculator's going to really do most of the work for you. You just have to recognize when to use them, that's all. So we'll just work some problems and you get the hang of it and see that using these inverse trig functions really isn't that tough. Especially if you have some facility with the original trig functions. Now, which of these expressions would be correct? We want to figure out the measure of angle J. Well, the sine of angle of J here would be opposite LK over KJ. So the inverse sine of that would give us the angle. What we want is KL over JK. Well, we got JK here, but that doesn't look like LK to me. So this doesn't look right. Here we have the tangent of angle J. Well, this is the arc tangent, but what would the tangent of angle J be? That would be opposite over adjacent. That's LK over JL. That's the tangent. So if we took the inverse tangent of that, it would give us back angle J. And it looks like we have the correct expression here. We can double check and take a look at what these are just in case. What's angle K? Okay, for angle K, the cosine would be the adjacent LK over KJ. Well, they've got JL over JK, so if we're going to do it this way, this should be the inverse sine, not the cosine. What about this one here? The sine of angle K is JL over JK. They put JL over KL. If we're going to do that, we'd be using the inverse tangent, not the inverse sine. So these two don't work either. This is the one that actually gives you the right answer, because the tangent is, in fact, of this angle, this opposite side over this adjacent side. That's what we have here. The opposite over adjacent. We take the inverse tangent of that, and that gives us back the angle. And just to see how it works, let's pretend this was one of our 3, 4, 5 triangles. It's obviously not to scale. That looks like kind of skewed for a 3, 4, 5, but suppose it was. Well, what would KL over JL be? 3/4, right? I think. Yeah. Here we go. If this was a 3, 4, 5 triangle, what would this angle here be? Well, we could take the tangent. Pardon me, that's not the angle I wanted. We want the figure out angle J. Then the tangent is 3 over 4. And we can punch that in here and take our inverse tangent. So that's 0.75. Well, I don't see inverse tangent here anywhere. We probably need to shift. There we go. 36.89. Okay. That sounds about right. What about angle K? Well, the tangent for angle K would be 4 over 3, wouldn't it? That's 1.33. So let's try that one. .53. Okay. And before we had about 36. And 36 and 53 adds up to 90. So it all makes sense. These two angles here should add up to 90. And just to see how these work, we just looked at the arc tangent and we got like 36 and 53. Probably 36 and 54 would be more accurate, wouldn't it? Or 37 and 53. Must be some round off error going on here, which happens all the time. What about using the arc sine? Well, the sine of J is opposite over hypotenuse, that's 3 over 5, or 0.6. And we take the arc sine of that. Well, same answer we got when we took the arc tangent, isn't it? Which is good, because they're all supposed to give us the same answer for the angle. For instance, if we want to use the arc cosine, well, the cosine is adjacent over hypotenuse. That's 4 over 5. That's the same as 0.8. And what's the arc cosine of that? Same answer. Okay, let's take a look at what the mistake is here. I'm sure it wasn't a student who did this. Undoubtedly a postal handler. What would the sine of 36 degrees be? That's usually the simplest way to look at it. Well, it would be opposite over hypotenuse. That's 7 over wx. If we took the arc sine of this, that would give us back our 36 degrees. Oh. Well, they took, well, that's just bizarre. They took 7, which is the length of WY, over WY. That's not a mistake, that's just careless. Nobody would really think that was a rule. That's just 7 over 7, that's 1. What sense would that make? But anyway, the WY here should have been WX. What about this one? Again, we have t here. What's the cosine of t? Adjacent over hypotenuse. So that's 15 over 17. That would be the cosine of this angle. So if we want this angle, we have to take the inverse cosine. And that'll be the measure of angle t. Well, what did he write here? 8 over 15. Well, that's the tangent. He could have used 8 over 15, in which case he could make this the inverse tangent of 8 over 15. That would give you this, that's opposite over adjacent. Or he could have, if you're going to stick with the cosine, you have to make it 15 over 17. If you're going to stick with 8 over 15, then you have to use the inverse tangent. So there's two ways to correct this, depending on how you want to do it. Have I mentioned yet there's more than one way to solve a math problem? So he could have taken the tangent of this expression, or, pardon me, the inverse tangent of this expression, or the inverse cosine of this expression. But the inverse cosine of this would not work. This one is intended to make you think about how much information you actually need to figure out various aspects of a right triangle. For instance, an angle on a side is good as long as the angle isn't the right angle, because you already know that there's one right angle. That's what makes it a right triangle. But aside from that one, if you know either one of the other two angles, that's why it always says if you know one of the acute angles and the side, that's enough. So if you know angle P and PR, you could solve the triangle. How would you do that? Well, how about you could use the sine or the cosine, because you know the hypotenuse. If you know the hypotenuse, then see the sine of angle P equals, pardon me, for instance with angle P, the sine is the opposite over the hypotenuse. That's QR over PR. PR is known, and we can punch sine of angle P, because we know angle P, and I guess you're supposed to put a measure in here, because after all, sine only works on actual numbers. So the sine of the measure of angle P is equal to this ratio. We know angle P, so we can compute the sine, and we're given PR, so we can find QR. We've got a hypotenuse and a leg. There's several ways we could find this here. We could use our tangent. We got angle P, yeah. We could use our tangent, which would be our opposite over this. We could also use Pythagoras' theorem. So knowing this, once we've got, I guess what I'm trying to say is, if we've got one side and the angle, we can find another side. And then we've got two sides in an angle, and we can just keep going like that. Because if you've got one side in an angle, then when you've got two sides in an angle, you've got another side in an angle from which you can find the other angle, and you're on your way. So as long as you can solve for one of the other sides with the information you've got, you can finish off the whole triangle. Suppose you know angle P and angle R. Well, our trig functions tell us about the ratios of various sides and hypotenuse. Once again, I'm stuck with a plural for hypotenuse. But just given an angle, without any other information, how in the world could we figure out what the lengths of the sides were? Or let's look at it another way. We know angle P and we know angle R, and of course this is the right angle. So we've got all three angles. Remember what we said about similar triangles? If all three angles are equal, we have at least similar triangles. They could be congruent, but they're at least similar, which means we can produce an infinite number of right triangles with the same angle at P and R. All we have to do is multiply by k, where k is any number. We've got an infinite number of k's, so we can produce an infinite number of similar triangles, which means that there's just absolutely nothing we could say about the length of any of these sides, because they could be anything. Once we pick a length for one side, we can easily determine what the other two sides have to be, but until we're given a definite number for at least one side, this could be any one of an infinite number of similar triangles, which would have the same angles at P and R. So this definitely is not enough information. And let's keep checking just to make sure we didn't make a mistake here. How about PQ and PR? Well, let's see here. Here's PQ and here's PR. Well, that makes sense, because PQ over PR would be the sine of this angle here. So we could take the arc sine of PQ over PR, that'll give us this angle, and then we can solve all the rest of the sides and the angles, because once you know one acute angle, you automatically know the other one. So solving for the angles is very easy. And this, we have angle P and then PQ. Well, that's exactly like what we had over here, except that we had the angle and the opposite side. Now we have the angle and the adjacent side. Well, that will be solvable also. We'll just use the cosine. So it looks like we're back to this one. The two angles just ain't enough. And the problem with given just two angles is that we can produce an entire army of similar triangles that would all have the same angle at P and at R, which means we have no actual information about the dimensions of these sides. And there's no way we can get any information about the dimensions of these sides unless we're given the length of at least one side. Now here's one that's going to use a little algebra, a little trigonometry. The perimeter is 16 centimeters. And so far I've just written everything in terms of x, because we don't know the length of anything yet. We just know that the length here is 3 times the width. So if the width is x, the length is 3x. And what's the perimeter? Well, it's x plus x over here and 3x plus 3x. In other words, x plus 3x plus x plus 3x. Or, obviously, 2 times x plus 2 times 3x (6 and 2 is 8x). That equals 16 centimeters. Now that we've got this, we could immediately solve for x. But we don't need to. Not yet. Eventually we will. But the interesting thing about this, suppose we wanted this angle. Let's call this alpha. That'll be different, right? We want this angle here. We've divided this rectangle up into 2 right triangles, so we can start using our trig functions for right triangles. Now we don't know what these sides are, but remember, take the tangent for instance, which is opposite over adjacent. We only need the ratio. We don't need the actual numbers. Now, this isn't too tough because the tangent of alpha is going to be opposite over adjacent. The x's cancel as long as x is not equal to 0. And if x was equal to 0, we wouldn't actually have a rectangle. So we're going to pretend what we really do, in fact, have a rectangle. So x can't be 0. The x's cancel and we get the tangent of alpha equals 3. So what would alpha be? Well, that's easy, right? We just did all that. It's the arc tangent, the inverse tangent of 3. What would that be? Well, let's take a look. All we have to do is punch in 3. We want the arc tangent 71.6. Which doesn't seem quite right to me. Now I had to double check my math. I guess it's my drawing that's not very good, because there's nothing wrong with what we did. So this is definitely 71.6, no matter how bad that looks. That's what it is. There's no way around it. Okay, so we've got an angle here, 71.6. We never even needed to figure out what these were. Now what's this angle over here? Well, that's easy. That's 90 minus. If we want the other angle, all we have to do is subtract this one from 90. And that'll give us 18.4 up here. And this we already know is 71.6. This is, of course, 90. And they asked us to solve one of the right triangles, which makes sense because they're congruent. We solve one, we solve the other one automatically. Now, all we have to do is find x and plug that in. And in fact, we already did that over here. It looks to me like x would be 2 centimeters. So over here we get 2, and this is 6. Well now, there's only one thing we haven't figured out. That's this right here. Well, we know this. So we could take the sine, or the cosine, or we could use Pythagoras' theorem. What would you like to do? I think the sine or the cosine is probably easier. Let's try the cosine of 71.6 degrees. That'll be 2 over BD, which we don't know yet. But we can figure it out quick enough, can't we? So let's start with writing it out so we know exactly what we're talking about here. The cosine of 71.6 degrees is going to be adjacent over hypotenuse, x over BD. What's the cosine of 71.6 degrees? Once we figure that out, we can multiply it by, I wrote this kind of dumb. Adjacent over hypotenuse, that's okay. But we now know what x is. It's 2. I think I wrote an x up in here. No. Just go ahead and put the 2 in. Now we have to solve for BD, and we get that BD equals 2 over the cosine of 71.6 degrees. And this kind of makes sense, so far anyway, because this number is going to be pretty small. Well, not real small, but it'll be less than 1 anyway, which will make the whole number greater than 2. but we're not sure how much greater than 2 yet. Let's check our calculator and see what it says. Now we have the cosine of 71.6 degrees, and what I should do is make sure that that's in memory. Okay, now I take 2, divide, memory reclaim, and see what we got. 6.33. Actually, I think that rounds off to 6.34. That's one way to do it. On the other hand, we could have done this. 2 squared plus 6 squared equals what? 8 squared. So we have h equals the square root of 40. What happens if we punch that into our calculator? Is there a square root here somewhere? Yeah, I think this is the square root side. 6.33. Okay. Looks like the same answer, just about. I got 6.34 when I rounded off. This would round off to 6.32. Try that again. I'm not sure why there's so much difference. 6.324. Yeah, it's just the way I rounded it. It was 6.324 and this is 6.336, so a few hundredths difference, but you get the same answer within reason. If you did it this way, you could have also, well, let's see, 4 times 10. So we could write that as 2 times the square root of 10, I think. That answer would probably also be accepted. In fact, I'm sure it would be accepted. And you may notice that the more you're learning about geometry, the more ways you can find to solve the same problem. So the better you get at this, the more ways you're going to see to solve any particular problem. It'll get to the point where your only confusion is, which of all the great ways I know to solve this problem should I use? Okay, here's one where you're under bridge, looking at a duck and figuring out exactly what angle to set your tripod at so that when you fire the shotgun, you get the duck. How would you do that? I'm kidding, of course. They're not asking you about shooting ducks. All we have to do to find this angle here is take the tangent of 7 over 12. It's pretty easy. Well, pardon me, the arc tangent. The tangent of 7 over 12. Pardon me, the tangent of this angle would be 7 over 12. So, yeah, let's call it alpha again, what the heck. The tangent of alpha is opposite over adjacent, or 7 over 12. Okay? That means that the arc tangent, the inverse tangent of 7 over 12 will give us alpha. And if we try that, and looks like they're about 30.5 degrees. But they got tricky. They want the angle of depression. That's always the angle that you make with the horizontal here. So your angle, if you're setting up your artillery, You want to fire at 30 degrees to hit the duck. On the other hand, if the duck was shooting at you, he would have to use 90 minus 30.5. And what's that, 59.5? I think that works. 30 and 60 is 90, so 30.5, 59.5. So this one would be 59.5. The important part was understanding that you needed to use the inverse tangent of 7 over 12 to get this angle. I guess you could have used, to get this angle, maybe we could have just used the inverse tangent of 12 over 7. What would that give us? Let's try it. Let's see what happens here. And we'll just punch that in. And then we want the inverse. Gee, I should have written it that way too. 59, same thing. And this is the inverse tangent. It's important to get that right, because the tangent of 12 over 7 is senseless. There's no such thing as a tangent. You can only take the tangent of angles. And I'm not sure why my calculator is getting slightly different answers different ways. They're off by a few hundredths either way. I assume it's round off error, I don't know. But it is equivalent. 90 minus this would be the same as this. Well, I hope this one wasn't too confusing. That's about it.